Hi, I'm Bob. Welcome back to the 5 Minute Econometrics, an econometric tutorial on fundamental concepts, identification strategies, and estimation methods. Today, we will explore one of the classical linear model assumptions, the No Perfect Collinearity assumption. The No Perfect Collinearity assumption states that there are no exact linear relationships among any of the explanatory variables in the model. An immediate example is that when we include both female and male variables in the model, we cannot estimate the parameters for both variables in a model with an intercept. The reason is one of the variables can be expressed as a linear function of the other variable, so it is redundant to include both variables in the model. We only need to put one of them into the model. When the coefficient of the variable is estimated, the coefficient of the other variable is also determined. What we have seen is the case of perfect collinearity for the dummy explanatory variables. So it is also called the dummy variable trap. Perfect collinearity occurs not only among dummy explanatory variables, but also in other cases. Here's an example. The outcome variable, college GPA, is associated with 4 explanatory variables. The students are asked how many hours they spend each week in 4 activities: studying, sleeping, working, and leisure. Any activity is put into one of the 4 categories, so that for each student, the sum of hours in the 4 activities must be constant. The model violates the No Perfect Collinearity assumption because the 4 explanatory variables sum up to a constant. We can express any variable as a linear function of the other 3. We should drop one explanatory variable from the model to avoid perfect collinearity. In simple regression, when there is only one explanatory variable, the No Perfect Collinearity assumption is sometimes called a sample variation assumption. The only explanatory variable should not take the same value for all its observations, so that it will not be perfectly collinear with the constant intercept. If the explanatory variable has no variation and has identical value for all observations, then it will have an exactly linear relationship with the constant intercept term. The No Perfect Collinearity assumption is also referred to as the full column rank assumption. We can write the explanatory variables and the constant intercept in the matrix form X. The matrix X will have the full column rank of k plus 1 if there's no perfect collinearity among the k explanatory variables and the intercept. That is to say, the columns of matrix X must be linearly independent. The full column rank assumption is the matrix version of the No Perfect Collinearity assumption. No perfect collinearity among the explanatory variables, or the full column rank of the explanatory matrix X, is the necessary condition to compute the OLS estimate for the parameters. We can see it clearly from the OLS estimator formula in matrix form. X transpose times X is a k plus 1 by k plus 1 square matrix, where k is the number of explanatory variables. Only when the matrix X has a full column rank of k plus 1 will the inverse matrix of X transpose times X exist. In other words, X transpose times X needs to be invertible to compute the OLS estimators, and it occurs only when X has a full column rank. Stata will omit one of the variables automatically if there is an exact linear relationship among any of the explanatory variables. For example, we add female and male variables to the model that relates US workers' log hourly wage to education. Stata will drop the male variable and report that it is omitted because of collinearity. It will estimate the coefficient for the female variable, which is around minus 0.19. It suggests that female workers earn 19% less than male workers on average if they have the same educational attainment. It is equivalent to saying that male workers' hourly wages are 19% higher than their female counterparts. We have discussed the No Perfect Collinearity assumption and its matrix version, the full column rank assumption for the population model. I hope it helps you better understand the assumption. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.